Good morning. Sorry for the delay. So I have a few announcements. The first of them is the quiz will be posted. I'll try to push it out today. So that's the quiz with the usual deadline on Thursdays. I'm also trying to push the feedback for lab 3 tonight. We'll see how it goes, but hopefully I can do that. So yeah, either tonight or tomorrow morning we'll push the feedbacks out. What else do I have? Oh yeah, and then course evaluations are out. So if you're watching this video, the recordings of this video, please pause here and go and do the evaluation. If you're attending the live event, please open a tab if you haven't already evaluated the course. Please open a tab and then leave it there. Once the course is done, please go ahead and finish it up. As I explained in my email, I really truly appreciate the feedback I get. So that's pretty much what I have. If there are no questions, let's start the lectures. Okay. So we were talking about caches. So we did some definitions with the terminology of caches. So just to recap, we said that we divide the cache into sets, and then each set has one or more blocks, and depending on how we do this mapping, we give it different names. So if each set has m blocks, we say the cache is m set associative, m way set associative cache. If there is only one set in the cache, then you have a fully associative cache. If each set has only one block, then we have a direct map cache. Now, once we have the sets in the cache, the answer to those three questions that we had, which is where to find my data in cache, where should I cache my data, and which data block should be evicted if there is no space, I can actually answer these questions. Once I have sets, there is a one-to-one mapping between each memory block and a set. So each memory block, now we're talking about memory blocks, have to go to one particular set. So there's a one-to-one mapping from memory blocks and sets. So let's say if you have a fully associative cache, it means that you only have one set. Well, every memory block is mapped to the same set. If you have, sorry, it's not one-to-one, but what I meant to say was for each memory block, we have a set in the cache that hosts that memory block. So, and that set doesn't change, right? Now, if you have a fully associative cache, well, you only have one set, so everyone is going to go there. If you have an m-way set associative cache, then for each memory block, you should know which set you're going to check. And if you have a direct map cache, then each memory block is going to go to one of those blocks in your cache. Now, we're going to actually now talk about how we can, like in hardware, how we can actually do this mapping. So I guess we saw this example in the previous lecture. Now, let's look at fully associative cache. So in a fully associative cache, as I mentioned, each there's only one set, so each memory block can go anywhere in the cache, right? Now, as a result, this guy, if I want to bring it to memory to cache this block, I have to check all my cache locations because it could be any in any of those, right? So how do I really know if I have cached this this particular memory block? So how do I know if this is cached? Well, I need tag, very similar to direct map cache. But how long should be my tag? Well, in this case, I need to actually hold the entire address as my tag, because this block could be anywhere in the cache because I only have one set. So it could be anywhere in this set. And the only way I have to recognize that I have cached this block is to tag that memory location, that cache, with the address of the memory block that I have. So I tag it, and then let's say, you know, I want to see if I have cached this block. Then I look at all my tags, and I see if I can find this address in my tags. If I see that address, then I look at my cache and I have the data. If I don't find the address in my tags, it means that memory location is not cached, and that's a miss, right? So the purpose of having this this tag is to identify if we hit in the cache or if we miss in the cache. So if we found the tag, it's a hit, we can use the data. If we don't find the address in our tag, that means that it's a miss, and we have to go to the memory to fetch the data. Very similar to direct map cache in previous slide. Here we have a smaller portion of address. We use a smaller portion of address as tag. The reason for that is in direct map cache, each memory is only mapped to one cache block or one set. In this case, just one block. So as a result, I already know the last 3 bits in this example. So I already know if I'm looking at this memory, this cache location, this 100, this basically means that the last 3 bits of the address is 100. So that I know. I don't need to tag my cache with that. I only need to keep the last 2 bits in my tag. So every time I get an address, I only look at the first 2 bits, and I try to find them in my tag. And I actually know which location I should look. I don't need to look at all my tags. I only go to this particular address, 100, and then I just search the tag. And if the tag matches the last 2 bits, that's a hit. If it doesn't, it's a miss. Now compare that to fully associative. In fully associative, if you get an address, you actually don't know where to look. You have to look at all the cache locations. So in this example, you will have to now compare your entire address with all the tags. So this should give you an idea. There is a huge cost with fully associative caches, because you have to check all cache locations and you have to actually have a bigger tag. However, it's more flexible. So each memory block could be anywhere. And this is good. This is flexibility. Why is this good? Because in direct map cache, there is only one location for you. So if that location is occupied, you have to evict that location and bring the new data. Maybe the location that you just evicted is a hot spot. Maybe it's a better idea to keep that location. But in direct map cache, you don't have any other options. You have to evict that to bring the new data. Whereas in fully associative cache, now you have an option. You can put your data anywhere in the cache, right? You're not bounded to a particular location in your cache. You can put it anywhere. So that's flexibility, because maybe one of the locations is a hot spot. You can preserve that location, and you can find among all the caches the one that is less used, for instance, to evict that and bring your new data. So it's more flexible, but at the same time, it's more costly, because now, first of all, you have to store a bigger tag. And second of all, for each search, for each check to your cache, you have to go through all your memory blocks, all your cache blocks, and then check the tag for all of them. Now, something in the middle is the Set-associative cache, where you don't just map it to one block or all the blocks, you just map it to M blocks. So you just focus your search to only few cache blocks. Let's say if you have a 4-way set-associative cache, you only have to check 4 cache blocks. And then that also reduces the number of bits that you're going to use for tag. So in the spectrum, the fully associative cache has the highest number of tags and the higher overhead for search. The direct map cache has the lowest number of bits and the lowest cost for search. And then Set-associative cache is something in between. It has some number of bits, more than direct map and less than fully associative for tag. And the search is also limited to M cache blocks rather than 1 or all. Okay, so here's another example. Let's say we have let's say this is our memory, and it has 32 memory blocks. So these are the addresses from 0 to 31 memory blocks I have. Now let's look at different caches and see where in the cache we should search. Let's assume that the cache size is 8. So similar to the previous example, direct map cache, each location is mapped to a single location. So if the size of my memory is 32 and the size of my cache is 8, that basically means that I have to get mode to 8 of my address. So 12 mode 8, that's 4. So that's the only location that this particular memory block could go. So here I have the set numbers. So because it's a direct map, I have as many sets as I have blocks. So I have 8 sets. And to identify which set I should look, I just take the mode 8, and I find my location. Let's say now this time we have a 2-way set-associative cache. Now, as a result, if I have a 2-way, it means that each set has 2 blocks. So how many sets do I have? Well, I have 8 blocks in my cache, 2 of them for each set. That means I have 4 sets, and each set has 2 blocks. So here I have the 2 sets. I just divided my cache into 2. So I have 2 sets. Sorry, I apologize. I have 4 sets. So I have 4 sets, and each one of them has 2 blocks. So these are set numbers 0, 1, 2, 3, 0, 1, 2, 3. So 4 sets. And as you can see, there are 2 memory blocks with set 0. And there are 2 memory blocks with set 1. And there are 2 memory blocks with set 2, 2 memory blocks, 2 cache blocks with set 3, right? Now, this time, I have 4 sets, so I get the mode by 4. So 12 mode 4, that's 0. So now I have to look at my set 0 to see if I can find the cache there. Lastly, if I have a fully associative cache, it could be anywhere. So there is only one set. All of the cache blocks belong to set 0. So my memory block could be anywhere. I have to search all of them. Now let's look at tags. For this one, I have 8 sets, so that would be 3 bits. So 3 bits I know about. I don't need to care. And I just look at the rest of the address, the 2 bits for my tag. In two-way set associative, I have 4 sets, that's 2 bits. So 2 bits for indexing and the rest of it for tag. With fully associative cache, I only have 1 set, that's 0 bits. So no index. All of the bits are used for cache. Okay, hopefully that makes sense. So yeah, I guess I'm gonna actually, because this is sort of hardware stuff, and for the interest of time, because I'm really behind, I'm gonna actually jump from how it's implemented in hardware. Hopefully what I explained makes sense in how we find it. If you're interested, definitely look at these. I can also link to my last year's explanation of how direct map cache or set-associative is implemented. So if you're interested, you can watch the lectures from last year. So I'm going to actually jump from them. Again, if you're interested, some of you actually may know about these from other courses that you're taking this semester. So for those of you, it should be fine. For those of you who aren't and are interested, watch the lectures. I will link to it on the YouTube channel, on the YouTube video when I post the video. Yeah, so these the slides just explain how it's done in hardware, which we can jump as I just did. Okay, so let's talk about effectiveness of cache. Hopefully we have an idea of how caches work. So suppose that you have a 2 megabyte and 8-way set-associative cache. So this is the size of your cache. This tells you that each set has 8 blocks. And let's assume that your physical pages are 4 kilobytes. So that's the setting that you have in your system, very typical of your system. Before moving on, by knowing the size of your cache and the set associativity of your cache, you can identify how many sets you have, right? So you have 2 megabyte data in your cache. Although no, actually there is one piece that is left, and that would be the block size of your cache. But anyways, so if I give you the block size, then you can actually tell me how many sets you have in your cache. Now suppose that your hardware is using low order bits of physical address to index cache, very similar to basically the examples that I walk you through. So basically this slide says, let's assume that whatever you just saw in the previous slides hold. Now what? Suppose that you have one process A, and this guy, for whatever reason, the operating system has given it, when the operating system was doing memory allocation, assigned in physical memory, physical pages to this process that are apart from each other by 256 kilobyte. So the first page is address 0, starting from address 0, let's say. The second page is starting from address 256. The third page starts from 512, and so on and so forth. So they're just, stacked on top of each other, and then there is a 256 kilobytes, empty holes between them. So whatever reason, this is how they are mapped to physical cache, to physical memory. Let's see what happens to this poor process when we want to cache its data. So now the question is, how much cache capacity process A can effectively use? So that's the question that I'm asking. Now let's do the math. This you have a 2 megabyte cache, and it's 8-way set associative. So you can divide 2 megabyte to 8. And that gives you basically the yeah, that gives you 256 kilobyte. If you divide 2 megabyte to 8-way set associative cache, so it's to 8, that's 256 kilobyte. And that tells you that every byte in your memory, every 2 bytes in your memory that are apart by 256 kilobyte, they'll be mapped to the same cache set. The reason is because this 8-way set associative, that's how it acts. It basically maps every 2 bytes that are apart from each other by 256 kilobyte and maps them to the same set. Now, if this process A, all its pages are apart from each other by 256 kilobyte, what does that mean? That means that all these pages are mapped to the same set. As a result, this process can only use one set of your cache. Out of all the sets in your cache, this particular process can only use one set. Right? So, what does that mean? Each set has 8 blocks, and assuming that I think the underlying assumption in this is that we're using the same block, the same what is it? The block size is basically 4 kilobyte. So when I have 8 weight, that means 32 kilobyte is all that I have in each set. And that's all this process can use. So this process is limited to one set and can only use 32 kilobyte of the 2 megabyte cache. And that's basically only 2% of the cache. So out of a 2 megabyte cache, because of the way I allocated memory to this process, my process ended up being able to only use 2% of the cache. This shows you the relationship between memory allocation and caching. So when we're allocating memory, maybe we should take care of caches as well. And that's precisely what many systems, many operating systems do. So this is an very famous algorithm called page coloring that is actually used in many operating systems to allocate memory. And what's the idea? So the idea is precisely the example that I just brought to your attention in the previous slide. We'll just color each memory block in physical memory. We color every, depending on our set associativity and the size of the cache, we color all the memory blocks that are mapped to the same set with the same color. So let's say, I guess 1, 2, 3, 4, 5, 6, 7, 8. Let's say this this particular cache. I guess we don't have. Yeah. So let's say this is the cache 1, 2, 3, 4, 5, 6, 7, 8, and let's say it has 8 sets. So I color all the memory blocks that come to set 1 with red, as you can see. All the ones that are coming to set 4 with yellow, and so on and so forth. Now, when I'm allocating memory to my application, so when the operating system is deciding how to do the mapping from virtual addresses to physical addresses, meaning that when you want to allocate physical memory to your application, you actually look, when you see 2 consecutive virtual memory blocks, you want them to get different colors. Because otherwise, these 2 consecutive virtual addresses, these 2 consecutive virtual blocks, if you give them the same color, they will be mapped to the same set, and then they have to compete with each other. So when you're running your application, you're going to go through your virtual address space, and if 2 of them are mapped to the same set in the cache, so if they both have the same color, when you cache them, they're going to compete with each other in one set, and that's bad. So you go to the example that I brought to that we discussed in the previous slide, and there would be contention, and that's what you want to prevent. So when the operating system assigns physical memory to virtual memory, it uses these colors, and it makes sure that 2 consecutive virtual ranges have different colors, and that's all you care. So if you look at this example here, each 2 consecutive virtual address has different colors. Generally speaking, you want to maximize the number of colors that you're using for each application. That means that you're spreading it in your cache so that they don't need to compete with each other. Because when you start running this program, you want this program to be as fast as possible. And the way you make it fast is to make them be mapped to different sets in your cache so that they don't need to compete with each other. So the algorithm is called basically page coloring. Okay, so now let's talk about possible sources of cache miss. If you remember, the whole point of this lecture when we started it was to bring down the average access time to your cache. And one of the big factors was the miss rate. So if you have a higher miss rate, that means that your average response time is higher. So how can you shrink it? First, you have to identify what are the sources of missing in the cache. The first one is compulsory misses or cold misses. These are the misses that you incur when you first see an address. So these are unavoidable because this is the first time you saw this address. There is no, I mean, if you had prefetched it, you probably will find it. But let's say you don't have prefetching, then, well, this is the first time you're seeing it. You shouldn't expect it to exist in your cache. So that's a compulsory miss, the first time you see an address. Now, Other than that, you might have capacity misses, meaning that, well, your cache is full and there's no space for a new memory block to be cached. And that's why you're missing. If you had more more cache, you probably would have hit in your cache. So this is when you miss in the cache because of the capacity of your cache. The other one is conflict or collusion misses. So this is basically the example of two memory blocks being mapped to the same set and having to compete with each other. So let's say if you have a direct map cache, and you have cached something in one of the sets, and now you have to cache another one. So this new one has to evict the old one. Next time you see the old one, you will have a miss. And that miss is because of conflict, because it was evicted by previous access. To solve this, you still can increase the cache size. If you increase the cache size, then you will have more sets. So the conflict on each set goes down. That's one. The second one, you can actually increase the associativity of your cache. In direct map cache, everybody is mapped to the same. So many memory blocks are mapped to the single cache block. If you increase direct map to two-way associative, you all of a sudden have two options, and that decreases the competition for each one of them. You have four-way associative cache. Now you have 4 blocks that they can compete, and that increases the chances of holding into a memory and not evicting it because of a conflict. So it decreases the conflict misses. And lastly, you have the coherence misses. So this is a miss that is caused by the fact that you have a multi-core system, and although you have the memory block cached in your cache, but it's invalid because somebody else has modified this. So these are the conflicts that you get because of cache coherence protocol. So these are the 4 major sources of cache misses. Okay, so next topic that we're going to talk about with regard to caches is the replacement policy. So far, all I alluded to was, you just look at the set that your block is mapped to, and then you have to evict one of them. Now the question is, which memory block in my set do I evict for a new memory to be cached? Now, if you have a direct map cache, then each set has only one block, so you don't have any more options. You're not going to choose between blocks. You only have one block in your set. So the question of which block to evict is answered easily. The same block in your set, you just evict it. You don't have any other options. Now, if you move on to other ones, M-way set-associative or fully-associative, now you have options, because in your set you have more than one block, so you can choose which one you want to evict. Now, one policy is to just randomly pick one of them and evict it. It's easy to implement, but probably has a poor performance, because maybe the one that you evicted is the hotspot, is the cache block that your program actually uses a lot. So by evicting it, you're basically hurting your performance. There are other ways of doing it. One of the mostly used ones is the least recently used policy. Basically, this policy keeps track of how frequently you access each memory block. And when it comes to eviction, it basically evicts the one that has been used least recently. So if I have one memory block that was accessed exactly in the previous cycle, and I have another block that was accessed 100 cycles ago, the one that was accessed 100 cycles ago probably is not going to be accessed in the future, so I can evict that one. So basically least recently used. I'm going to actually talk about these eviction policies when we talk about paging, demand paging. In the next lecture, we'll cover eviction policies. So wait for then, so more on this later, but just for now, know that there are different policies that you can use when it comes to eviction. Now, another question you have to answer with caches is what happens on a write? So most of the examples so far were on reads. If you read a memory block, you check your cache, you see if it is a miss or hit. If it is a hit, then you can read the data. If it is a miss, you go to memory to bring your data. Fine. But what happens on a write? What happens if you want to write? Now on write, you have two options. First, let's say if you hit in the cache, so you can find the memory that you want, the memory block that you want to write to in your cache. What should you do? Should you just write to the cache, or should you also go and write in the memory as well? Because this time it's just you're writing, it's not reading. Do you have to also go to the memory? So there are two methods. One is write through, which basically says write to both of them. Write to your cache and also go to the next level memory. If it is another cache, then write to the other cache. If it is the memory, go and write to the memory. So this is cache, this is write through. So you write through all the, all the memory levels that you have. Now this one, the advantage is if you have a read, if you want to, if you want to evict in future, let's say you want to evict this block that you just wrote to, you can safely evict it because you know that the content of this cache has been actually written in the memory. So it's safe. You can evict it safely. So when you have a miss, then it doesn't result in another write because you have already written the content to memory. So it's safe, evicted. The downside is it just takes time, takes more time. Writing to your cache is faster than waiting for the write to propagate through the memory hierarchy. So it's on a write, you pay the cost, but when it comes to read, there's no cost. In particular, when it comes to evictions, you don't need to do anything. You just evict that memory location. The other approach that you can take is called write back. So in this one, you only write it in the cache, but you have to remember that you wrote this in the cache and not in the memory. So you usually have a dirty bit associated with each cache block, and you set that dirty bit. You say, I have written in this memory, in this cache, and I have to remember this. Now, later on, if you ever want to evict this cache, then you have to write it in the memory. So on evictions, now, you have to pay the cost. So in this one, you're paying the cost on the write. In this one, you're paying the cost on evictions. So the downsides, well, the read misses will require a write back. You have to write it. And it's a little bit more complex because you have to introduce the dirty bit. And then when you want to evict, you have to look at the dirty bit and all of that. So it's a little bit more complex. you have to pay the cost in the read. So what are the upsides? Well, the first one is that let's say you keep writing to a cache block, to one particular cache block, you keep writing. With write through, all these writes have to go to memory, right? So you write the first one, you write A, and then you write B to that address, then you write C in that address. So all A, B, and C, they have to be written in the memory as well. With the write back, you write A in the cache, then you write B in the cache, and then you write C in the cache. And when you want to evict, you only write C in your memory. You don't write A, B, and C. You only write the last, the most up-to-date version to the memory. So it reduces the bandwidth to the memory. It's kind of like a buffer. You write all of it, and then the last write is the one that will be written to the memory. So that's one. You're basically reducing the memory bandwidth. The second one is that, well, the other benefit is basically you're not going to wait for the DRAM to be written to continue your program. So your writes are basically faster. Now, which one to choose? If you stare at these two, you'll realize that depending on your application, one is better for you than the other. So if you have an application that writes a lot, then cache the write back method is your to-go-to, because it saves you bandwidth, and you're basically writing a lot, so you're not reading much, hopefully. So you're not going to pay this cost a lot. So you're just writing. Now, if your application has only few writes and mostly reads, then write through is the best for you, because you want to have the minimum latency for your reads. You don't want to spend a lot of time on your reads. So this one is better. And then you have very infrequent writes. So it's fine to hold the processor hostage during those writes, because you just have few of them. Okay, so that's that. Now, we said all of this, first of all, because caches are very commonplace in all systems. Distributed systems, multiprocessor systems, uniprocessor systems, caches are everywhere. In web, you have caches. In databases, you have caches. Like, caches are everywhere, basically. Every time an engineer, a computer systems engineer, wants to increase some performance somewhere, the first thing that they should think about is caches. Can I use caches? And usually the answer is yes, and you can actually come up with good caching strategies to improve the performance. Now, as engineers, especially as kernel developers, you would ask, wait a second, I'm translating addresses for each memory, and as I just saw in previous lectures, it actually is very costly to do the translation. If I have like a multi-level page table, I have to access my memory multiple times, and that's just ridiculously expensive. How can I bring the cost down? Well, you probably can use caches, and that's basically precisely what is being done in most, or maybe all, your laptops, tablets, cell phones, and etc. So you actually can cache the previously translated addresses. If you go through the pain of translating a virtual address to a physical address, why not caching it? Just cache this translation, somewhere, that this virtual memory is translated to this physical memory. And if later on you need to translate the same address, then you can use your cached translations. And that's the main idea. Now, good idea. We have to check first to see if there is some sort of locality. If you remember, caches are only good if you have some notion of locality, spatial or temporal locality. Let's see if we actually have that. So yeah, okay. So I guess I should have just walked through the slides. So yeah, I talked about those, that, you know, translating address is expensive and we want to make it faster, and caching is the way to go. Now, our page tables are here, right? And accessing main memory is just super expensive, and coming to main memory is super painful. So we basically want to cache them, cache the translations here. Very similar to caching in L1, L2, and L3. To speed up our program, we want to cache the translations very close to the processor, so that each translation is done super fast. Okay, so yeah, that's the main idea, to basically cache the recent virtual to physical translations. Where do we cache them? The hardware structure that we use to cache the translations is called Translation Lookaside Buffer, TLB. The bigger your TLB is, the faster your system is. Very similar to all your other caches, right? If your L1, L2, L3 are bigger, then your system is faster. If your TLB is bigger, then your system is faster, because it's actually caching something very important, which is address translations. Now, again, so I wanted to come to this point. Do we have any locality when it comes to address translation? If you think about it, each page, like in modern, you know, in many systems, is 4 kilobytes or 16 kilobytes. So there are 16 kilobytes in each page. So if you're reading 1 byte in 1 page, there is a huge probability that you're going to read another byte in this page. So you definitely have a spatial locality, right? So again, that's that. The other one is, yes, you also have temporal locality, because if you have, we already saw that you have a spatial and temporal locality in memory accesses. If you have a spatial and temporal locality in memory accesses, well, you have that same localities with their addresses, because you're using those addresses to access those memories. So if you're accessing a particular address, you're going to actually access, you know, addresses around it. And when it comes to translation, all you need to do is to translate the virtual page number, not the entire address. Offset you are using, it's just the physical and the virtual page to physical page translation. So you basically sort of have the spatial and temporal locality. Now, there is a little bit of variation on whether or not accessing the memory is a data access, or if it is code access or instruction access. With regard to instructions, you are usually doing sequential accesses, right? So that gives you definitely frequent accesses to the same page. So you definitely have a spatial access with regard to instructions. You probably don't have much temporal. You might have it if you have a loop, for instance. You go to the same instruction again and again. So not only the data that you're accessing, you know, you might access the same data again and again. You're also running the same code. If you're going through a loop, right, the set of instructions that you're executing is limited. So in a window of time, you visit the same instruction multiple times. So that's that. So you have a spatial and temporal with instructions. Now, if you're accessing, let's say, your stack, you still have some locality again, right? Because your stack is you're probably gonna access the data in your stack inside your functions. So you probably have both temporal and spatial accesses. Now for the rest of the data, you might have less page locality. You might access data that might be mapped to different pages in your memory, but you still could access the same data again and again. So you probably don't have much spatial locality with data, but definitely could have temporal locality. So let's say the example the killer example for this is like an array, right? Your array is mapped to some page, and then you keep iterating through all the elements again and again of that array. So you actually have a spatial locality in that case. And in the case of an array, you probably have also a spatial, because if you access one element, you're going to access the other element. Now, if you have a big file that is mapped to multiple physical pages, then you probably don't have a spatial locality. The reason is those pages might not be mapped to consecutive pages in your physical memory. So if your entire file is mapped to consecutive pages, physical pages, then you will get a spatial locality with regard to those pages as well. But usually that's not the case. Your physical pages are scattered through the physical memory, so you probably don't get spatial locality. But again, you're going to get temporal locality, right? You might actually use that file many times. So you're translating. You're going to go to a bunch of pages in a window of time. So you're going to get temporal locality. So overall, it's feasible to use caches for address translation, and it actually makes sense because we do have locality. So we're going to do that. Now, there are so many questions that you have to answer now, which we'll be doing in the coming slides. Let me check time. Okay. Let's see where TLB sits in our system if we want to have one. So TLBs will be sitting right before the page tables. So every time that you want to access, every time that your CPU produces a virtual address, you're going to go to the TLB. You will check your TLB. If you find that translation from virtual to physical addresses, you get a hit, then you use the offset to go and access your physical memory and get your data back. If it misses, then you're going to go to page table. If you find that virtual page that you want to translate has a valid translation, so if it is valid, then you basically do the translation, you bring the translation that you just did, and you cache it in your TLB, and then you use it to also access physical memory. And if it is invalid, then you raise an exception. In this point, operating system should, get involved, and depending on the access, the operating system has to make a decision whether or not to, update the page table as the example of, expanding heap or expanding stack, or maybe this is actually a bad access and you have to, you know, terminate the process and throw out an error. Okay, so that's one thing actually. Before moving on, this picture is kind of like deceiving. It shouldn't be. The question I would raise and I would want you to think is, where is this page table actually? So where is it? And the answer, you'll soon see that the answer is that it's actually here in physical memory. So this page table is in the physical memory. So missing in TLB means that you have to go to physical memory. I'll talk a little bit about it when I talk about how the whole thing is implemented in hardware. But basically, missing in TLB means that you have to go to your page table, where page table is in your memory. So you have to go to your memory. Okay, so you need to keep your TLB consistent with your page table entries. This is super important. And that's also true when it comes to, you know, caches, right? We had to, with last level, with L1, L2, and L3, you know, we wanted to keep our caches consistent with the memory. So if something changes in memory, I want that change to be reflected in what I have cached. Now, the same concept is true with TLB. If operating system, so here I have 3 examples. Let's say operating system reduces the permission of a page. So let's say I had this virtual page translated to this physical page, and it had read and write access. Now, let's say I have reduced the permission to just read. I took away the write access. What should happen to the TLB? So if I have cached this translation in my TLB, that this virtual page is mapped to this physical page with this access permissions, if I reduce the page table entry, I actually have to invalidate my TLB. In early computers, there was no way of invalidating a particular entry in your TLB. So as a result, you had to flush the entire TLB because you didn't have any, you know, hardware support to invalidate a particular element in your TLB. In modern architectures, the hardware gives the operating system the ability to invalidate particular entries in the TLB. So you have to do that. So you have to find the translation in the TLB and then invalidate it. Say this is no longer true. So basically you don't have it in the cache anymore. Next time the access happens, you have to go and look at the TLB. Now, what happens if we add permission? Let's say it was a read page, so the page had a read access in the page table entry. Now the operating system elevated the access to read and write. What should we do with the TLB? In this case, you don't need to do anything, really. The reason is when the access happens, your hardware goes to the TLB and sees that the access permission is only read. So if the process wants to write, the hardware is going to say, no, you don't have that access. So the hardware is going to raise an exception. And when the exception happens, then operating system gets involved. And the operating system could actually tell hardware that everything is fine, update the TLB, and let the process go because it's updated, right? So you don't need to get involved immediately. You can wait and see if the program ever, you know, writes, uses this new access, and then when that happens, you can manage it. The third example here is, what if you know, a page table entry becomes invalidated, meaning that let's say I have evicted a page. So this virtual page 5, was mapped to physical page 10 with an access pattern, and then my memory got full, and I had to evict a page, and I picked this particular page, and I evicted it back to the hard disk. So at that point, operating system comes and updates the page table entry and puts an invalid in that entry. What should happen to the TLB if we update a page table entry to invalid? Well, the same thing that happened with the reduction in permission, now that the page table entry is invalidated, you also have to invalidate the TLB. Because if you don't, then hardware will go to TLB and thinks that the translation is still valid. So again, in old days, you will have to flush your TLB, entire TLB. In modern architectures, you only need to go to that particular entry and make it invalidated. Now, what about writes? So, you know, all the things that I said about write back method, where you make things dirty and then you have to take care of it later on when you want to evict it, the same things happen here as well. So usually TLB entries don't have access bit. So okay, so me. Yeah, I thought that I had this slide in the caches, but turns out that I don't. So I guess I moved on. I didn't walk through this slide thinking that I have it in the, and I would talk about it in future, but turned out that I don't. So let's talk about it. So this is a page table entry in an x86 system. This is a 64-bit system. Now let's look at all the elements here. So again, remember, this is a page table entry. So basically it has to have the translation for us, saying that where this virtual page is mapped to. Now, the big chunk of it is actually the physical page number. So this is where the translation happens. Where this virtual page is mapped to, well, here. These bits are used for translation. Now, bits 40 to 51 are reserved, as I mentioned. So, sorry, I haven't mentioned this. So they're not used. So they exist in the page table entry, but they're not used. Let's look at the first ones. The first one is valid bit. So this is whether or not this translation is valid. The second one is read-write access. So do I have read access, or do I have read and write access? The third one is the ownership of this. So is the owner the user, or is the owner the kernel? The fourth one is write through option. Do I have a write through cache, or do I have a write back cache? So this is where I store the bits here. Can I actually cache this, or can I not cache this? So again, you can actually disable cache for certain pages. You could say, don't cache this page for whatever reason. Now, here comes the accessed bit. This A bit here is accessed bit. So what this is every time you access a page, you sort of want to know that this page was accessed. You will soon realize that it's actually super expensive to keep track of all the accesses. But what you can have, and what systems usually have, is the first time you access a page and the hardware misses in TLB, so the translation is not cached in TLB, so you have to go to page table to look at the translation. Well, when you're looking at the translation, it means that you want to access that page. So when hardware looks at the translation, it also sets this bit to 1. And then later, the operating system can use this data that this cache was this page was accessed when it wants to make a decision who to evict. We will come back to this later on, but as of now, all we care about is this is a bit that hardware sets, and it would indicate that this page has been accessed by the program. And then you have the dirty bit, which we just talked about. So let's say if your program writes to a page, so you can actually set the dirty bit to 1, saying that this page has been written to. Now, this is important because it might be a file in this page, and you might not want to write the file right away to your hard disk. So you set it to 1, you say, okay, I changed the content of this page. Later on, when this page wants to get evicted, you write it to the hard disk. Now, here, your brain should go bang, 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 because I'm using the same concept when I talked about caches. I talked about cache for main memory. We had dirty bit. And now we're using main memory as a cache for hard disk. The concept is the same, right? You have multiple levels of memory, of storage. So each one acts as a cache for the second one. Now memory acts as a cache for your hard disk, for your permanent storage. And now that's where the dirty bit comes handy. If you change the content of a page and you might want to write it back to the memory, you can use this to the permanent storage, you can use this dirty bit. Then you have the large page, which I guess we talked about super page. Oh, we're going to actually talk about him. I mentioned the idea of super pages. Now we're going to touch based on that with TLBs as well. So this is a bit that you use to say this translation is for a super page. It's not just for a normal page. So this is where you can actually set. And then there is the global, there is the copy on write, and so on and so forth. Okay. This one actually is interesting. The last one, NX, no execute. So the thing is, interestingly, for whatever reason, with the 32-bit systems, x86, 32-bit, they didn't have any bits reserved for giving a page execute permission. So it was all implemented in software because there was no hardware support for it. I don't know why. In my opinion, it was dumb. But later on, AMD, when they prototyped the 64-bit, the 32-bit was prototyped by Intel. But then AMD took the upper hand and did the prototyping for 64-bit. One of the things that they first did was adding this execute bit to the page table entry. So again, if you look at page table entry in a 32-bit system, you actually don't find any bit to give a page execute write. So you have the read and write bit, but there is no execute bit to indicate that this page can be used only to execute or for execute for that matter. So it had to be handled in software, which is more costly. Now in the 62-bit, they actually added it, and they added it to the last one, sort of rubbing it to Intel's face, in my opinion. But anyways, so that's interesting. Now let's go back to address translation caching. Okay, that was a detour. Now let's talk about this accessed bit and dirty bits when it comes to TLBs. Now with TLBs, we generally speaking, we don't cache this access bit. So again, a TLB entry is a cache of the page table entry, right? We're caching the address translation. Now, when we cache it in TLB, we might not want to cache all the information in the page table entry. One of the information that we're not interested in is this accessed bit. So usually this access bit is not cached. And as I explained, usually when you miss in TLB and the hardware has to go and fetch the translation from page table entry, that's when the hardware sets this bit in the page table entry, but not in the TLB. So what happens is the first access, you set it in the page table entry. The further accesses in the future, they're going to just go to TLB, find the translation, and use it. And there is no access bit in TLB, so it won't be set anymore. So basically, what that means is only the first access you usually get the hardware to set this access bit, and not the future ones. So this is something very important that we will come back to when we talk about eviction and demand paging, right? So keep that in mind. We'll come back to it. It's important. What about dirty bit? Dirty bit is actually cached. So a TLB entry does have a dirty bit. So if you miss in your TLB, then you have to walk through your page table, and there you can actually set the dirty bit in your page table entry. You can also set it in your TLB as well. The reason you do this is because the reason you have to have the dirty bit in TLB is that it could well be that your first access is just a read, so you don't get to set the dirty bit in your TLB, so it's just read. You cache the translation in your TLB. Now the second access is a write. So in the second access, you have the translation in front of you in TLB, so you might not want to go back to the page table entry. That's where you actually can set the TLB dirty bit to 1, and you usually actually go back and do that to the actual TLB entry as well. So basically on every write, you do change the dirty bit. Now, why do you want to cache? Why do you want to have the dirty bit in TLB if you're gonna go to the page table entry and set it? Well, the reason is you just do it on the first write, and the consecutive writes that you do, you don't need to go and set the dirty bit in page table entry. You just do it once. You set the dirty bit in page table entry. You set the dirty bit in your TLB, and now any future writes, you don't need to go back to the page table entry because you already have indicated that the content of this page has changed. So future writes, you can just look at your TLB entry and see that the bit is set to 1, that tells you that the dirty bit is also set to 1 in your page table entry. So you save yourself the pain of going to page table entry and set it to 1. So you basically don't do anything. You don't go to the page table entry anymore. So for the first write, you set it in TLB and page table entry. For future writes, you just look at your TLB, you see the dirty bit is set to 1, you don't go to the page table entry, you just use the TLB entry. Yeah, and this way you're basically saving memory bandwidth, because going to page table entry means going to physical memory, means, you know, using bandwidth, using memory bandwidth, which is something that you don't want to do. Okay. Now, the question is, as always, do you really need, you know, the hardware to have this bit in your page table entry and also the TLB? So very similar to that execute bit that I just talked to you about in the we talked about it, that it didn't exist in, you know, 32-bit system, that this page has execute right, and software was actually able to handle that. It was slow but still possible. That's why it was added in the 64-bit system to just make it more efficient and make the hardware be able to handle checking the execute permission. The same is true with dirty bit. The answer is no, we really don't need it. We can, as a operating system, we can actually handle not having dirty bit for page table entry and the TLB entry. But as you will see, it just makes it super slow if you don't have it. You still can to manage, do the functionality, but it's just harder. How do you do that? Well, all you do is just make every page have read-only access. And what that means is on every write, the hardware has to wake up the operating system, say, oh, this process wants to write to this page, and you have indicated that it has only read access. What should I do? And that's where the operating system can be notified that this page has been written to, so that the operating system can know that it has to, you know, eventually put the data back to the hard disk. So you don't really need that bit. You can simulate it in software. But again, as you can see, this is super slow to be interrupted for each write. But it's possible. Now, you can ask the same question with the access bit. Now, I haven't told you why we need this access bit. I guess I have indicated that we'll need this for eviction policies, because we want to know, you know, the least used page. When we want to evict the page that has been used the least. So how do we know how much a page is used? Well, access bit is our to-go to. That's how we know that this page was accessed. Now, if we don't have that bit, we can simulate it. How? We just make all our pages invalid. So basically the same idea. Here we downgraded the access bit from read-write to read-only. Now we downgrade one step further. We make everything invalid. So now for every page access, the hardware is going to wake up the operating system, say, oh, something went wrong, and the operating system wakes up and laughs and says, no, nothing is wrong. I just wanted you to wake me up to, you know, keep track of accesses to pages. Now I know, go and execute the file, execute the program. So again, super slow, but possible. I mean, altogether, you should answer this question fast, because we don't really need page table altogether, right? You can implement page table in software. You can do the translation in software. Again, super slow, but possible, right? So now that you can do the entire thing in software, it's kind of silly to ask, do we need this particular bit in the page table entry when we altogether don't need page table? I mean, when I do this need, we really need it for performance, but theoretically we don't need it. We can do everything ourselves in software. But that's that. Okay. Now let's talk about this caching. So I kind of like made everything rosy so far. That like, yeah, you just add. Oh, I'm over time. So sorry. Gosh. Let me talk about the rest of the lecture in the next one. Sorry. I went over time. Yeah. Okay. So please, I repeat one more time. If you haven't done the course evaluation, please, if you can, do it now. If you're watching, just do it right now after the lecture. If you have attended the lecture today, again, right after this, when we end this lecture, please do so. So thank you so much. Take care, be safe, and talk to you on Thursday. Bye-bye.